Okay, let's go ahead and get started. Just administrative announcement. I guess there have been several requests, so you can all have an extension on the problem set until Monday if you like. Okay, so having finished our discussion of scalar QED, what I want to move on to now is the discussion of spinors in quantum field theory. And in order to begin our discussion of spinors, what I really want to do is really step back a little bit and revisit a little bit what we mean when we think of a particle in quantum field theory. So the starting point of quantum field theory is the idea that we should find a theory that unifies both special relativity and quantum mechanics. So in particular, what that means is that when we try and describe the theory, the group of symmetries of the theory, namely the Poincare group, the set of translations, along with Lorentz transformations, should be realized as unitary operators acting on some Hilbert space, because that is how symmetries are treated in quantum mechanics. So actually, first I should apologize. I have a cold and I'm starting to lose my voice, so I'm not going to be able to speak very loudly. So you should all feel free to come closer to the front of the room if you can't quite hear me, okay? Because the quieter I speak, the longer I'll be able to go without losing my voice completely, okay? So this will be a very dramatic class where you all will have to lean close and listen very intently to what I say. I actually had to I gave a seminar once and I'd completely lost it happens once a year that I lose my voice, usually around this time of year after a long semester of lecturing. And I gave some seminar and I completely lost my voice, and it was the most dramatic seminar I've ever given because everybody had to lean forward and listen very intently to what I was saying. Okay, good, thank you. Okay, so what does it mean that the Poincare group is realized as some set of unitary operators on a Hilbert space? Well, mathematically, what that means is that in the quantum field theory, we describe it as a theory of quantum mechanics, where the Hilbert space is a representation of the Poincare group, otherwise known as ISO 3,1. How many of you have seen the mathematics of representations of groups? How many of you have seen that language before? Okay. So we're not going to use too much heavy-duty representation theory in this course. But let me just introduce you to a little bit of the language so we're all speaking the same language. In general, if you're given some group G, okay, and what is a group? A group is just a set of some set of elements along with a multiplication rule. So that is to say, some way if you hand me two elements of the group G, say G and H, then you can multiply them together to find another element of the group G times H. And a group is a set with a multiplication rule that has several nice properties. For example, there's an identity element 1, which when you multiply it by something, you just get that something back again. And for every element of the group, there's also a multiplicative inverse, G inverse, so that G times G inverse is equal to 1. Okay. And a representation of a group is a vector space, or more generally a Hilbert space, and a map that associates to each element of the group some unitary operator acting on this Hilbert space. So a unitary operator for each element of the group, and this unitary operator acts on the Hilbert space, And it respects the multiplication law. So that is the defining property of a representation. It is a set of operators acting on some Hilbert space that respects the multiplication law of the group. So U of G times U of H is U of G times H. Okay. So you, of course, have already encountered many group representations in this course and in your life, although you may not have bothered to call them as such. So let me just give you a simple example. So let's consider a real scalar field. And then the Hilbert space, in the limit where this theory is free, non-interacting, is given by, say, 1 particle states, 2 particle states, and so forth. And let's just consider the 1 particle states that are labeled by some momentum k. And if you know the mass of the scalar field, then that means given a momentum k, you actually have the 4 vector k mu, because k0 is then determined by the other 3 elements of k. So if this is a single particle state, then we know how the various Poincare generators act. In particular, under a translation, T, so let's let T be a translation by some amount A, so that it shifts the position vectors by some 4 vector A mu. And the unitary operator associated with the translation, acting on a single particle state, is just proportional to the identity element. It's just the phase e to the I k dot A. Right? That says that some momentum state under a translation just picks up the correct phase. And more generally, under some Lorentz transformation that's given by some Lorentz matrix lambda that takes x mu to lambda mu nu x nu, the unitary operator is just the one that rotates the 4 vector k in the way that 4 vectors rotate under a Lorentz transformation. Okay. So that's how single particle states transform. It's easy enough to think about how 2 particle states transform. Okay. So how do 2 particle states transform? Well, we saw that the single particle states transform in this very simple representation of the Poincare group in terms of these unitary operators. And it's easy enough to generalize this to 2 particle states. So for example, if you have a 2 particle state describing 2 particles with momenta k1 and k2, and you act on it with a Lorentz transformation, well, I'm just going to suppress all the indices there. Hopefully it's clear. The 4 vectors k1 and k2 will each just individually transform under a Lorentz transformation. Okay. Or if you want to think about this a little bit more explicitly, so if you want to think about this as U as a matrix acting on some vector space, then it's the matrix that takes the 8-dimensional vector, whose 2 components are the 4 vectors k1 and k2, to another 8-dimensional vector, which is the original vector multiplied by some block diagonal matrix, whose entries along the diagonal are this Lorentz matrix lambda, and which has zeros in the off diagonal. And of course, you could look at 3 particle, 4 particle states, and so forth, and see that in each case, the Hilbert space is some representation of the Poincare group. Okay. So there's a substantial difference between the properties of the single particle states and the multi-particle states, however. Okay. In particular, for the single particle states, the unitary operators that act on the Hilbert space are not block diagonal. Okay. Whereas for the multi-particle states, we've found a basis in which the unitary operators are block diagonal. And when we talk about representations, we make an important distinction between representations that can be put in a form that is block diagonal and those that cannot. Okay. So in particular, a representation which can, by some change of basis, be put in some form that is block diagonal is called reducible. And otherwise, the representation is irreducible. And sometimes, just as a shorthand, we refer to an irreducible representation as an irrep. Okay. And the nice thing about group representations is that any representation can be regarded as a sum of a bunch of irreducible representations. In the same sense that a two-particle state can be thought of two separate one-particle states, each of which are assembled together and into one large vector and then acted on by a bunch of block diagonal matrices. It turns out, it's just a theorem about group representations, that any representation, subject to certain assumptions that I don't want to go into, but essentially any representation can be written as a direct sum of a bunch of irreducible representations. Okay. And we see here that the irreducible representations of the Poincare group play a special role. They're the single particle states. Okay. So the claim then is that this is a different way of thinking about particles. In particular, a particle, that is to say, a single particle state, is a unitary irreducible representation of the Poincare group. So earlier on in this class, we have defined particles as, in terms of raising and lowering operators that are extracted from some fields or something like that. This is kind of a much more essential definition of what we mean by a particle. And in fact, you could take this as the fundamental definition of what a particle is, an irreducible representation of the Poincare group, and from there develop your theory of fields, rather than working as we have in this class, starting with fields, and then from that understanding the group theory properties. Okay. So if you want, this could not just be a claim, this could be a definition of what we mean by a particle. It's some sort of localized excitation that can be moved around and acted on by the Poincare group. And the fact that the important point is that a general representation will not be interpreted as a single particle state, but might be interpreted as a multi-particle state. And it's only those irreducible representations, those where you can't block diagonalize these unitary matrices, that are viewed as single particle states. Question?
So the same holds for interaction theory also?
The same holds in interacting theory.
So we
Yeah.
can write, for example, a two-particle state, we can write it as block diagonal.
That's correct. That's correct.
Three to four particles.
That's correct. Yeah. I mean, in some sense, the reason this is, this is a lovely way of starting, this is not how we've structured this course, but one could have started the definition of a particle as an irreducible representation of the Poincare group and then worked from there. Okay. It's somewhat less intuitive, it's a little bit more abstract, but it's an equally kind of well-defined way of thinking about the definition of particles. Okay. Yes?
The particle is the operator or the state? So,
The particle is, I guess when I say is a unitary irreducible representation, I mean the Hilbert space of states that describe a single particle. Okay. Of course, as we'll discuss, the operator phi, which creates or destroys a particle, will also transform in some way. But what I mean by a particle here is this Hilbert space, the set of states that describe a single particle. Okay. Good question. Yes. Yes. No, but remember that remember that we sort of demanded when we talked about the LSZ formula and the one of the things that we demanded is that you should be able to have widely separated multi-particle states in your Hilbert space, even in the presence of interactions. Now, their properties might change. So, for example, it may be that particles form bound states and so on and so forth, but there still should be some kind of well-defined particles. Okay. And you should be able to have multi-particle states built out of them. Okay. It won't be a simple Fock space, of course, but there should still be multi-particle states.
Yeah, but would that mean that the diagonal terms small and we can ignore them on this sort of separate?
I mean, when I talk about a multi-particle state, implicitly what I mean is that they're so widely separated that their interactions can be ignored. Yes. Yeah. Good question. Okay. So far we've seen that scalar particles are very simple representations of the Poincare group. But the point is that more complicated particles are then defined by more complicated representations. So, for example, if you want to describe the Hilbert space of a photon, then the single photon state is described both by a momentum and a polarization vector. And under a Lorentz transformation, both the momentum and the polarization vector will change. And they'll change in the usual way associated with the way that vectors transform under Lorentz transformations. Okay. So we see that a scalar is given by an irreducible representation which has 1 degree of freedom per momentum mode k, whereas a gauge field, a U1 vector field, is given by an irreducible representation with 2 degrees of freedom per momentum. And so, if one wants to understand the types of particles that one can have in nature, then one can really reduce this to a mathematical problem that is the classification of possible representations of the Poincare group. The classification of possible unitary matrices which will obey the multiplication rules of the Poincare group. Okay. And this is a mathematical problem that was solved by Wigner, who showed that all possible representations of the Poincare group fall into a finite set of classes. Okay. So in particular, he showed that the unitary irreducible representations of the Poincare group are labeled by 2 numbers. In particular, they're labeled by a positive number that I'll call m squared and a half integer that I'll call j that can take values 0, 1/2, 1, 3/2, so on and so forth. And these have the property that for fixed momentum, momentum here being the eigenvalue of one of the spatial translations, p, there are 2j plus 1 independent degrees of freedom if m squared is strictly bigger than 0, and precisely 2 independent degrees of freedom if m squared is equal to 0. Okay. So, for example, the states with m squared greater than 0 will describe massive excitations with spin, such as the scalar field, the electron, a massive vector field, such as the W's and Z bosons, and so forth, whereas the massless representations at spin 1 would be described by a photon, at spin 2 would be described by, an example would be the graviton, and then, in principle at least, this classification would allow for higher spin particles as well. I should mention, just as an aside, that in Wigner's classification, there are other irreducible representations that he found, corresponding to particles with negative mass squared or with continuous spin, that don't appear to be realized in nature, although I think it would be sort of interesting to speculate about them. And so some people do speculate about whether there are interesting theories of particle physics that might be realized in nature based on these other representations, but we don't have any evidence of this. Okay? So in this class, at least, we'll focus just on these representations, these sorts of particles. Any questions? Yes?
Somehow this mathematical problem accounts also for gates.
Absolutely. So it's the fact that when m squared equals 0, there's this reduction in the number of degrees of freedom, okay, that is sort of crucial. Okay. Yeah. So for example, you can see that when you have a spin 1 particle, j is equal to 1, you would have 3 degrees of freedom if m squared is bigger than 0, and 2 if m squared is equal to 0. Okay. And likewise with the graviton, there's a reduction down to 2 degrees of freedom as well for spin 2. Yes, question.
Does it mean the limit m going to 0 continuous? Some degrees of freedom has to die out.
That's right. That's right. The way that works is that certain degrees of so there's a couple different ways of thinking about that. One way of thinking about it is that if you study, for example, a massive vector, then in the limit where m squared goes to 0, there's sort of 3 different polarizations of a vector for finite m squared, and they completely decouple as m squared goes to 0. Okay. Yeah. And they become basically a scalar and the one that we've studied so far. Okay. And that's basically the Higgs mechanism. But that's not something that I want to go into quite yet. Okay, good. Okay. So one of the things that's important to notice is that in these representations, the unitary operators act on the fields as well as on the states. So, for example, if you have a real scalar field phi, then under a translation, which takes x to x plus a, where a is some 4 vector, then phi goes to u of t inverse phi of x times u of t, which of course is just phi at x plus a, where u of t is the usual expression in terms of the momentum p that generates translations. And likewise, under our Lorentz transformation, u of lambda acting on phi, so phi is an operator, it's an observable, and so as usual, the states transform by multiplication by the unitary operator, the observables transform by conjugation by the unitary operator, and so u inverse u phi is then equal to phi at x prime, okay, where x prime is the transformed value of x after you act with this Lorentz transformation. life gets a little bit more interesting if you think about not scalar fields, but particles with spin. So in particular, under a Lorentz transformation, this gauge field A mu will go to some transformed gauge field, which accounts for the fact that A mu has a Lorentz index. So in addition to the space-time point x transforming, as it does under a Lorentz transformation, the index A of the gauge field will transform as well. And so the point that we really want to keep in mind is that for a particle with spin, we really have to keep track of two different ways that the particle is transforming under a Lorentz transformation. Both the point x is transforming, the place where you evaluate this field operator is transforming when you do a Lorentz transformation, but the index also that labels the different fields that make up this, that label the different fields is transforming as well. In particular, in the case of a gauge field, it's described by a 4-vector, so it's transforming like a 4-vector. And in general, a particle with spin is described by some sort of multiplet, that is to say, a collection of fields that I'll label by some index capital A that will transform under a Lorentz transformation by the conjugation of some unitary operator, which will be some matrix that I will call L, that'll be a function of lambda times phi b, and in addition, the space-time point will transform as well. So just as with a vector, though that's a set of 4 quantities that transforms under a Lorentz transformation by moving the point at which the vector is evaluated, as well as some rotation of the index. In general, a particle with spin is going to be a set of quantities phi a, where a runs from 1 up to some number, that will mix with one another under a Lorentz transformation. And the way that they mix is given by this matrix L.
So the matrix L, that is not in the 4-vector representation, right?
It is not. So in this case, it's the 4-vector representation. In this case, it is not the 4-vector representation. It's going to be some other representation. And what I'm going to do today is classify the possible representations it could be in. But the important point is that it is a representation in the sense that it has to satisfy the group multiplication law. Okay. So the multiplication of two of these L matrices with one another, which I've written out here explicitly in index notation, has to respect the group multiplication law. Okay. Okay. So what we need to do now is figure out what possible matrices L are allowed. Now, in finding representations of a group, it turns out that it's easier to construct not representations of a group, but representations of what is known as the associated Lie algebra. That is just a fancy way of saying that it's easier to construct the representations of infinitesimal elements of the group. sometimes people use a fancy mathematical language and say that this is a representation of the Lie algebra as opposed to the Lie group. Now, there are certain cases where actually the representations of the Lie group contain a little bit more data than is contained in the Lie algebra. This is probably not something that we'll ever have to worry about in this course, so I'm just going to forget about that for now. But there are cases where algebras and groups are not quite the same thing. So the case that you are all familiar with is the case of the rotation group SO3 as opposed to the complex group SU2, okay, where there are slight differences between the representations of SO3 as opposed to SU2. So in particular, the representations of SU2 allow for spinors, whereas the representations of SO3 do not. Okay? And it's the fact that in quantum mechanics, states are obey a complex superposition principle that means that the correct symmetry group is SU2 rather than SO3, which allows for spinors in nature. Okay. So what I'd like to do now is understand what the algebra of the infinitesimal generators of the Poincare group look like. Okay. So some of those infinitesimal generators are things that you know and love, namely the generators of momentum and rotation. And so now I'd just like to generalize this a little bit. Okay. So in particular, let's first think about a translation. So a translation takes some point x to x plus a. And so in particular, if you think about some function of x, it takes it to that function evaluated at a shifted point. And now if you want to consider an infinitesimal generator, you take a to be very small. So this then can be Taylor expanded. And at linear order, you just get the derivative of a contracted with the derivative of phi contracted with the 4 vector a. Okay. So what that means is that there are 4 generators of translation typically denoted P, which are just given by, well, draw them with a lower index, I times the partial derivative with respect to x mu. And that I is completely conventional. It's so that when we write these down, when we write down the corresponding quantum mechanical operators, they'll be Hermitian as opposed to anti-Hermitian. So whether or not one thinks the generators of a Lie algebra are Hermitian or anti-Hermitian generally determines whether you're a physicist or a mathematician. Slightly more interesting are the Lorentz transformations. So that takes x mu to lambda mu nu times x nu. And what I would like to do is then expand this in the case where lambda is very close to the trivial Lorentz transformation that doesn't do anything. So I'll take lambda mu nu and expand it as the identity matrix, the Kronecker delta symbol, plus some infinitesimal generator that I'll call delta omega mu nu. And then x mu goes to x mu plus delta omega mu nu x nu plus higher order terms. Okay. And one of the things that you showed in either the first or the second problem set of the semester is that delta omega is an antisymmetric matrix. In particular, it has only 6 degrees of freedom rather than a full 16, as you might think for some 4x4 generic matrix. Okay. Do you remember this? This is something you showed on one of your problem sets? Okay, good. So, how does the scalar field transform Well, some function of x will go to that function evaluated at lambda times x, which can then be Taylor expanded, and you get that function of x plus delta omega mu nu x nu d mu phi of x plus higher order terms. Okay. And what I will actually do is I will move my indices around a little bit. I'll lower this index here and raise this index here. And then I will interpret this operator here as the differential operator that generates a Lorentz transformation in the same way that this operator here was the differential operator that generated a translation. Okay. So that means that the Lorentz transformations are generated by 6 generators that can be taken to be that I will call, actually what did let's see, I'll try and be consistent with my notes, that I will call L mu nu, that are just I, where that's that same I as I introduced above, just a convention, times x mu d nu. The only subtlety here is that I need to take into account the fact that this delta omega is an antisymmetric matrix, so I need to subtract off x nu d mu. So that in general, under a Lorentz transformation, phi will go to phi plus delta omega mu nu contracted with L mu nu acting on phi plus higher order terms. So this formula for L at first sight might appear to be a little confusing, but in fact it's something that you're very familiar with from your studies of rotations in both classical and quantum mechanics. So in particular, let me give a particular name to one of these. So let's take L12. That's I times x1 d2 minus x2 d1, which is otherwise known as, which is otherwise known as J3, the generator of angular momentum where you rotate around the z-axis. So this expression for L mu nu that I've written here is some sort of generalization of the usual formula in mechanics for the angular momentum vector expressed as the cross product of the position and momentum vectors, where I've just used the fact that the momentum vector as a generator of translations is I times the gradient. Okay? So I could write that as I times the gradient. Okay? So this antisymmetric combination of mu and nu here is just a generalization of the cross product to 4 vectors instead of 3 vectors. And there's a precise sense in which this is true. If you study differential forms, it's called the wedge product rather than the cross product. Okay. So these are then the 10 generators of the Poincare group. The 4 translations and the 6 generators of the Lorentz transformations. Okay. And a general element of the group can be found by exponentiating these infinitesimal generators of the algebra, namely P mu and L mu nu. Okay. So, for example, some translation would be given by the exponential of e to the I a mu d by d x mu, and some general Lorentz transformation lambda would be given by an exponential of I times some parameters delta omega mu nu times x mu d by d x nu. Okay. And I can even leave out subtracting off that thing where the two indices are interchanged if I use the fact that omega is an antisymmetric two-index tensor. So what we now need to do is work out the group multiplication law. Okay. So the group multiplication law will then imply some set of commutators of the infinitesimal generators P and L. Okay. So these are completely straightforward to work out, given the expressions that I've given you for these infinitesimal generators. Okay. So remember that P is just a partial derivative. Partial derivatives commute with one another, so P commuted with P is equal to 0. Question? Oh, I'm sorry. Yeah, I shouldn't have written it that way. You're right. Good. Thank you. Yeah. I guess I should really write U of lambda or something like that. Although, yeah, I'll just use that. Yeah. Write it like that. Good. Thank you. Other questions? Okay. Yes.
So we use the scalar fields to obtain the
I called them scalar fields. I really just meant a function. Okay. So any function phi would transform in this way. Okay. And the point being really is the following. Okay. So in general, what I'm looking for is something that obeys this set of relations. Okay. And so what I want to do, so these differential operators P and L are the things that describe the transformation of the point. And what we're going to need to do is understand what these matrices are that describe the extra transformation of the index. Okay. But those matrices have to obey the same algebra that the group generators that describe the transformation of the point do. Okay. And so I'm working out that algebra, and then we'll see, hopefully by the end of the class, what that tells us about how these multiplets of fields phi A have to how they transform into one another under a Lorentz transformation. Yes. Good. Any other questions? Okay. Okay. So what does the algebra look like? Well, two translations just commute with one another. What about the commutator of a Lorentz transformation with a generator of a translation? Okay. So let's just work that out explicitly. There's two factors of I, one for the L and one for the P. And then we have x mu d nu minus x nu d mu, and that has to be commuted with d by dx rho. And all of the derivatives commute with one another, so we only need to take into account the commutators of, say, this x here with that derivative, or this x here with that derivative. And what do you get? Well, from the so the commutator of an x with the derivative, so the commutator of x nu with d by d x rho is equal to delta mu rho. I've raised the rho index here, so that will give you a g mu rho times delta nu, and then minus g nu rho d mu, and with an overall minus sign out front. So that's just equal to I times G mu rho P nu minus G mu nu P rho. So this is the rule for how a vector transforms under a Lorentz transformation. Okay. So in particular, P mu, the generator of translations, is a vector, and what do vectors do for a living? They transform under Lorentz transformation. Okay. So I haven't proven it to you, but it's easy enough to show, and if you're not convinced, I encourage you to check it for yourselves, that this is the general rule for how a Lorentz 4 vector transforms under an infinitesimal Lorentz transformation. So in particular, under a Lorentz transformation, V mu goes to V mu plus goes to, well, lambda mu nu V nu. If you expand that out, then you'll get precisely this term over here for the leading piece in the limit where that Lorentz transformation is very close to the identity. Yes, question?
This left G mu nu should.
Oh, I'm sorry. That's a G mu. Yeah, that's a G nu rho P mu. Sorry about that. Thank you. Good. Okay. And there's only one commutator left to compute. This one is a little bit more work. So I'm not going to bother to work it out for you explicitly. You can already sort of guess what the answer is. The commutator, so remember that these Lorentz transformations include rotations. The commutator of a rotation with a rotation is a rotation. So you should expect that the commutator of a Lorentz transformation with a Lorentz transformation is another Lorentz transformation. And indeed, that's exactly what you'll find. Let's see. The only slightly annoying thing is that there are a million different indices to keep track of. But if you just work it all out completely explicitly, it's just working out a bunch of those derivatives, what you'll find is a sum of 4 different terms, which involve all of the various different permutations where the indices in one of these L's can be contracted with the indices in the other L. Okay.
So just the
Yes.
commutator of a translation, but twice, just like on each of the indices, essentially.
Sorry, say that again? Yeah.
Like, you would take the commutator.
It's,
with the
oh yes, I see what you mean.
indices.
Yes, that's right. That's right. That's right. It's a little bit, that's right. I think that's right. Yeah. I mean, yes, that's right. The point, yeah, that's a good way of saying it, actually. The point is that this rule up here really just tells you how a Lorentz index transformed. And a Lorentz transformation itself is a quantity with 2 indices. Okay. So what you get is the sum of 2 different terms determining how each of the 2 Lorentz indices transform. So you could think of this L mu nu as being the same as this L mu nu here. And then there's 2 terms, one of which here, which tells you how the rho index from this guy transformed. And the other here tells you how the sigma index, that guy, transforms. Good. Okay. That's a nice way of saying it. Yes.
Maybe we can relate this fact with the point that you made in the previous class that the rotation needs some displacement, some small displacement.
That's right. That's right. Yeah. That's right. Good. Okay. Now, so this is just the algebra of operators and how they act on spacetime. But in a QFT, these various Poincare transformations should be generated or should be given by unitary operators that are generated by some Hermitian operators that act on the Hilbert space of our quantum field theory. So just to keep things clear, well, not too clear, I wouldn't want to keep things too clear, but to keep things a little bit clear, what I'm going to do is I'm going to make a distinction between the operators P and L that act on the points in space-time, these differential operators, and the operators that act on the Hilbert space of the system. So for example, I'll write the unitary operator coming from a Lorentz transformation as the exponential of I delta omega mu nu, where omega mu nu are the parameters that define that Lorentz transformation, times some set of unitary operators m mu nu, where these 6 operators m mu nu are antisymmetric in the mu and nu indices, and they obey the Lorentz algebra. Okay. That is to say, they obey this same algebra up here that the L's obey. And likewise, the unitary operator that generates some translation will be given by e to the I AP, where the p's also now are Hermitian operators that obey the algebra that we derived above. So I'm being sort of careful to distinguish between the unitary operators M and the differential operators L, because in general in quantum field theories they will be different, because M will have to include the transformation properties of the Lorentz index. But I've been a little sloppy and I'm just using the same symbol P here for both the Hermitian operator on the Hilbert space and the differential operator I d by dx mu, because in fact in the quantum field theories we'll study, they're exactly the same thing. Okay. The momentum operator is really always just I d by dx mu. So the question then is, how will a general field with spin transform under an infinitesimal Lorentz transformation? So again, we consider some set of field operators labeled by an index A, one for each point in space-time, and say under a Lorentz transformation, they will transform by conjugation by this unitary operator. And so this is going to be phi A of x plus, so if you just insert this expression for u of lambda and you expand to linear order in delta omega mu nu, then you'll get the commutator of phi of A with the operator delta omega mu nu m mu nu plus higher order terms that we can neglect in the limit where delta omega is very small. Okay. Is that clear? If you just took this u of lambda here, you wrote it as 1 plus I times this business here, you would get a 1 minus I times this and a 1 plus I times this, and that the 1s would give you this, and the leading term would give you this commutator. Because there's a minus sign coming from here, where the m is before the phi, and a plus sign coming from here, where the phi is before the m. Okay, good. Is that more or less clear? And then this is supposed to be equal to LAB times phi at the point x prime, or phi evaluated at the point lambda dot x. Sorry, with an index b here. Okay. And what is phi evaluated at the point lambda dot x? That's LAB times phi at x plus phi b at x plus this operator I delta omega mu nu L mu nu acting on phi evaluated at the point x plus higher order terms. So the operator L is the thing that keeps track of how phi change, this set of fields change just due to the transformation of the point in space-time. And these operators, these matrices LAB, will keep track of how the index rotates. So what we need to do then is expand LAB as delta AB. So the Lorentz transformation lambda is very close to the identity. And so that means that we should be able to transform. We should be able to expand this, these matrices LAB very close to the identity. And I'll just give a name to those expansion coefficients. I'll call them S. Okay. They have a mu and nu index, which you need to keep track of depending on which Lorentz transformation you do. And they have an A and B index that acts on the fields. Okay. And so if you then plug that up into here and compare it to this expression here and factor out a delta omega mu nu, you'll see that phi goes to phi plus delta phi, where delta phi is I times delta omega mu nu times the commutator of phi with m mu nu, where this commutator is the sum of two terms. There's this term here, which just keeps track of the way that the space-time point changes under a Lorentz transformation. And there's a second term, which keeps track of how the index of phi changes under a Lorentz transformation. So if you had a real scalar field, then this second term would not be present. And this would just be the usual statement that under a Lorentz transformation, phi just changes a little bit by the action of this differential operator. So, but if you have a field that has some sort of intrinsic spin, then that means that this index A will run over some set of values, and these matrices S have to be present to account for the fact that the different components of this set of fields will transform under one another. Okay. So in quantum mechanics, a similar sort of thing happens when you consider, say, the hydrogen atom, where you have both orbital angular momentum and intrinsic spin angular momentum. Okay. So when you keep track of the angular momentum of, say, an electron in the hydrogen atom, you need to keep track of both its angular momentum state as it spins around the nucleus, and you have to keep track of its intrinsic spin. Okay. And that's essentially what these two different terms are here. But the important point, and the thing that we're really going to use, is that because both M and L satisfy the Lorentz algebra, that is to say, satisfy the algebra of infinitesimal Lorentz transformations, so does S mu nu. And in particular, all we need to do now is determine what sort of finite n by n matrices S we can have that will give you a representation of the Lorentz group. Okay. So S is a set of finite, let's say, n by n matrices that obey the Lorentz algebra, namely, so S mu nu, S rho sigma is G mu rho, S nu sigma plus dot, dot, dot. And so what I'd like to do now, in the last 20 minutes or so of class, is to convince you that, in fact, you already know the answer for what S has to be. Because we can fairly easily reduce this to a problem that you've already solved in your quantum mechanics classes. Before I do so, let me pause and see if there are any questions.
When you say that the P operator is derivative,
Yes.
this is also true in the case that you have an electromagnetic field because the momentum goes to the derivative plus the
So yes, it is. That is true. Yeah, I mean, yeah, no, it's still the case that the generator of translations is the derivative operator. The point is that when you couple a particle to electromagnetism, if you want to make it gauge invariant, then the dynamics is not given just in terms of the generator of translations, but instead of some modified generator. Okay? But it's always true that the generator of translations is given by P. It's just that the action might be more complicated than just simply, you know, the standard kinetic term. Yeah. Good question. Good. Other questions? Okay. Okay. So, in order to understand fields with spin a little bit better, we actually need to understand what sort of finite n by n matrix representations of the Lorentz group are allowed. Okay. So what I want to do then is write out the commutation relations of the Lorentz group in a little bit more detail. Okay. So this, what was this? This was I, G mu rho, M nu sigma, minus the thing where mu and nu are interchanged. Again, minus the thing where rho and sigma are interchanged. I want to write these out in a little bit more detail. Okay. In a way that will hopefully make a bit more physical sense. Okay. So what I want to do is consider rotations and boosts separately. Okay. So in particular, what I'd like to do is remember that the rotation generators are just those Lorentz generators where both of the indices of m are spatial. Remember that m12 was the rotation around the z-axis, x3. So I'll just define these ji's. So that's an epsilon ijk, mjk. Okay. There's a 1/2 there because there are actually two terms in the sum. Okay, so ji is the rotation around the I direction, and there's a 1/2 there because there's two terms that you sum over here. So, just for example, J1 would be epsilon 123 M23 minus epsilon 132 M32. Those two things are just the same because the m's are antisymmetric. So J is the generator of angular momentum. And I'll just define K to be the other three components of M. Okay. So what are these guys? So the M0i's are the things that look like x0 d by dxi minus xi d by dx0. This is something that mixes time and space. So just as the j's are the generator of the 3 rotations, the k's are the generators of the 3 boosts that mix the 3 individual spatial directions with time. And then it's a straightforward exercise to go ahead and write out the commutation relations explicitly in this basis. Okay. So in particular, 2 of them are things that you can immediately guess. So the rotation generators obey the usual rotation algebra. The commutator of J with K is just completely determined by the fact that the boosts are given by a vector. K has a vector index, and all vectors do for a living is transform under rotations. So that means that the commutator of a J with a K is equal to a K. And the only slightly curious thing is that the commutator of 2 boosts is a rotation. Have you guys seen that before? Okay. I was considering giving you a problem set on your next problem set where you verify that explicitly, but the problems, there's so many good problems that I just couldn't, I just didn't have, it seemed cruel and unusual to give you another problem on top of that. But if you haven't done that, I encourage you to take your 2 favorite boosts in 2 different directions, calculate their commutator, and see that you get a rotation. Okay. So this makes it look like the representation theory of the Lorentz group is very close to that of the rotation group. Okay. And in fact, we can make this analogy between the Lorentz transformations and rotations much more explicit. So in particular, what I'd like to do is define now a vector n, which is the linear combination of a boost and a rotation. I'm going to give up the hermiticity of my operators, so n is no longer Hermitian. But the advantage of using these Hermitian operators, so the commutator of a j with a j is j, j with k is k, and k with k is j. And so this particular linear combination of j and k here that I've written has the property that the n's completely decouple from the n daggers, and they each individually obey the SU2 algebra, the rotation algebra. Okay. So that means that if you're willing to use this basis of non-Hermitian operators, then the representation theory of the Lorentz group completely reduces to the representation theory of the rotation group. Mathematically, we say that by saying the Lorentz group, SO31, is essentially 2 copies of the rotation group. Okay. Now, I should really put this in quotes here, because when we think about SU2, we usually think about Hermitian operators. Here we have non-Hermitian operators. So sometimes people say this is, give a different name to that group, they call it SL2C, okay, instead of SU2. But that's not something that we really need to worry about. The point just is that we now have 2 SU2 algebras, and we can go ahead and write down the representations given our knowledge of the representations of the rotation group. Okay. If you don't remember the representation theory of the rotation group, don't worry. There's some lovely problems on it on the problem set for next week. Okay. Let me just remind you that a representation So the representation theory of SU2 is like one of those things that you should just have at your, you should be able in your sleep to do the representations of SU2. Okay? And after your next problem set, you will be, okay, if you aren't already. Okay? So a representation of SU2 has an integer number of dimensions. Well, every vector space has an integer number of dimensions, so that's not so surprising. But there is one irreducible representation for each integer n. Okay? So, and we give different names to those representations. So, for example, the spin 0 representation, otherwise known as the 1 representation, is the representation where all of the j's are set equal to 0. Okay. That's the trivial representation where the unitary operators are all just equal to 1. The spin 1/2 representation, or the 2 representation of SU2, is the one where the ji's are given by the Pauli matrices. And there are representations of integer n. So, for example, the spin 1 representation, the ji's are given by 3 matrices, and so on and so forth. Okay. So one of the problems on your next problem set is one where we reproduce this classification. It's very easy if you haven't done it before. Okay. Like I said, you should be able to do it in your sleep. I should mention that there are really two different notations that people use when people label these representations. People either label them, as I have done here, by the spin of the representation, or they just label them by the dimension of the representation. So the 1 of SU2 is the same as the spin 0, the 2 is spin 1/2, the 3 is spin 1, and so on and so forth. I tend to use this language, although I believe your book uses this language. Okay. In any case, they're easy to go between one another. Okay. And so we now see that a representation of the Lorentz group is given by a pair of representations of SU2, because you need to choose what representation the n's are and what representation the n daggers are. Okay. So in particular, and then given such a representation, different sort of particles will be given by choosing the multiplets that we described above and just choosing the S mu nu to be the finite n by n matrices that are given by this choice of a pair of representations of SU2. So different particles correspond to different representations. So for example, if you take, so usually we're going to label these representations by a left and a right SU2, okay? So sometimes people will say SO31 is written as an SU2 left, which is the n's, times an SU2 right. Okay. And then we label the representations by specifying a pair of integers, one for the SU2 left, one for the SU2 right. So the simplest one would be the one which transforms trivially under both SU2 left and SU2 right. So that will describe a scalar field. The next simplest representation will be one where all of the Lorentz transformations in the left are given by Pauli matrices, and the ones on the right are given by just 0. So that's a spinor, and in particular, It's referred to as a left-handed spinner. Correspondingly, if the n daggers are given by Pauli matrices and the n's are given by 0, then you have a right-handed spinner. And then there are more complicated representations where both the left and the right-handed elements of the algebra are given by, have some non-trivial form. Okay. So, in particular, something where you have both the left-handed and the right-handed guys acting as Pauli matrices. This is a representation with 4 degrees of freedom. You have a two-dimensional vector space for the left, a two-dimensional vector space for the right. So it's a representation of the Lorentz group with 4 degrees of freedom. So it probably won't surprise you if this is the vector representation. And indeed, that's how it works out. Okay. Maybe in the well, maybe I should pause here and see if there are any questions. Okay. Yes.
The Dirac field is for
Yes. No. The Dirac field is actually a pair. So although this was not obvious, this is something we'll develop next week. The Dirac field was a 4-component spinner. But if you remember, we wrote it as a 2-component spinner up top and a 2-component spinner down on the bottom. Those were left-handed and right-handed spinners, respectively. So Dirac spinner is not the 2-2 representation. It's the 1-2 representation plus the 2-1 representation. Don't worry, we're going to do that. We're going to work that all out next class.
These two representation can mix right and left, cannot mix left and right.
That's right. So, you know, when the Lorentz group is just the product of the two SU2s. It's an SU2 left times an SU2 right. So they just don't mix with one another. I mean, in order to understand, yeah.
It's not a irreducible representation.
It's not a.
Irreducible.
This is an irreducible. This is irreducible.
But it don't mix the left.
That's correct. Yeah. Maybe I'm not quite sure what your question is.
Irreducible should mix because.
Okay. Here's an important point. When I say SO31 is SU2 left times SU2 right, that doesn't. They're not. It's not block diagonal, right? It is not the case, right? So the thing that is block diagonal is the Dirac spinner. This guy is not, you know. So the Dirac spinner is this guy. Okay. So you know, people usually will often write it with a little direct little plus with a circle around it right there. Yeah. The important, and this is a very important point. When I write this formula, you know, this does not mean that a general rotation matrix is written, you know, like in a block diagonal form with an SU2 on the top and an SU2 on the bottom, okay? Which is what you would have if you had a reducible representation. Okay. It's more complicated than that. I mean, it's because, you know, in order, right, I mean, this was the way that you constructed these guys out of the boosts and rotations. Yes, I mean, it will mean that these representations, the left-handed spinner and the right-handed spinner on its own will have some very funny properties. Okay? They'll have some funny reality properties. That's what we're going to explore next week. Okay. So sometimes we distinguish between various different kinds of spinners. The 4-component spinners that we saw in the beginning of the semester are known as Dirac spinners. These are known as Weil spinners. They're also Majorana spinners. So, you know, everybody's got a spinner named after them. Okay. Maybe one of the things that I'd like to do just in the last minute or two is just make contact with our previous notion of spinors in non-relativistic quantum mechanics. Okay. You've already met spinors before, and so you should hopefully expect that these sorts of spinors that we've met here will reduce down to the spinors that you know and love in non-relativistic quantum mechanics. Okay. Well, how do you get non-relative? What do you do in non-relativistic quantum mechanics? Well, to go from not relativistic quantum mechanics, quantum field theory, to non-relativistic quantum mechanics, what you do is you just forget about Ki. Okay. So that means that Ni is equal to Ni dagger. And so what is a left-handed, what is, for example, a scalar? So a scalar, well, that's still just going to be a scalar in when you forget about the Ki's. But let's now think about the more interesting case of a left-handed spinor. Okay. So this is something which transforms as the 2 under SU2 left, the 1 under SU2 right. But when you let n equals to n dagger, SU2 left and SU2 right are both just rotations. Okay. Another way of saying this maybe a little bit more explicitly is if you ask how one of these representations transforms just under a rotation, well, the left and the right-handed SU2s both transform the same way. So a rotation, and maybe this is a good way of saying this, the SU2 rotation is the diagonal subgroup sitting inside this SU2 left times SU2 right. Okay. You just forget about the K's. This SU2 left was J plus IK, SU2 right was J minus IK. You just do a J, it does the same thing on both sides. Okay. So what does that mean? That means that if you do a rotation, the 2-1 transforms in the tensor product representation. Have you guys seen tensor products, more or less? You'll see more of them on your problem set this week, don't worry. Okay. So it just transforms in the 2, because 2 times 1 is 2. And same with the 1-2 representation, which means that in non-relativistic quantum mechanics, left-handed spinors and right-handed spinors are the same thing. They're just what you call spin 1/2 particles of non-relativistic quantum mechanics. So what we've learned here is that the inclusion of special relativity to quantum mechanics means that the spinors of quantum mechanics now come in 2 different flavors. They can either be left-handed or right-handed. Okay. Yes, question?
Can you restore the coefficient in the Ki so I'm not saying something divided by the speed of light so we can neglect the Ki?
Sure, great. Let's do that. Yeah, do your dimension. If you did dimensional analysis, angular momentum, right. You would need to restore a speed of light in order to determine the difference between the two. But, you would have something like Ji plus I times 1 over the speed of light times Ki. So that if the speed of light is taken to infinity, then the Ki would go to 0. And why is that? Well, the Ki's came from an M0I up here. 0 is a time, so it's like T d by dx. And T and X are related by a C. Yeah, I mean, where you put the H bars is really like, I mean, this. Yeah, I mean, people sometimes put H bars in there. I haven't, Right. I mean, strictly speaking, when I say that in the two representation, where is it? You know, people sometimes put an H bar here. You know, they put an H bar over 2. Okay, been a little fast there. Yeah.
So group theory is a general framework. We're going to see quantum mechanics and relativity in a separate way.
Yeah, well, you know, group theory appears everywhere, right? I mean, group theory is the theory of symmetries, right? And those symmetries in quantum mechanics are unitary operators. Rotations are symmetries. Poincare symmetry. Everything's, you know, group theory is the theory of symmetries. And group representation theory is the theory of how symmetries act on vector spaces and Hilbert spaces. And so if you have a framework such as quantum mechanics where the space of states is a vector space, then the study of symmetries in quantum mechanics is the study of group representation theory. And you know, I'm in your problem set, you're going to do a lot of mucking around with SU2, and the reason being that, you know, you want to get fluent in all of this stuff not just for dealing with spinors, but also later on in this course when we study the standard model and stuff like that. All of this group theory is going to make a reappearance. Good. Okay, I'll see you on Tuesday.